Okay, let's take a look at Chapter 24, the nutrition chapter, and Objective 3, which involves temperature regulation and calorie counting. So let's go ahead and jump on in. Body temperature regulation. So thermoregulation is another word for regulation of body temperature. Core body temperature is going to be around 99.7 to 99.5 degrees Fahrenheit. It's a little bit higher than what you're normally used to hearing. You're used to hearing like, oh, body temp's 98.6. But on the inside of the body, it's a little bit higher. ATP production by the cells throughout the body produces about 60% of the body's heat. So when we talked about our cellular respiration equation in the previous objective, where we mentioned, you got glucose plus oxygen produces carbon dioxide, water, and ATP, and heat. So heat's on the end of that too. That's what you would call in chemistry an exothermic reaction, also known as a combustion reaction. That's what that is. Oh, through negative feedback. Okay, you have this handout in your packet there. So if you start, to kind of like showing you homeostasis here, if you start up here with number 1, where we have a problem where body temperature is too low. So this is our stimulus. This is our problem. Body temperature is low. Y'all, we've done this I don't know how many times. So let's just kind of talk about it again. Temperature receptors in the hypothalamus stimulate heat-producing mechanisms. So what's that going to do? That's going to talk to your blood vessels, and it's going to talk to your muscles. So for blood vessels, those arteries and veins are going to be constricted, conserving that heat loss. And then your muscles are going to involuntarily shiver, because shivering, when muscles contract, they generate heat. The other thing, if you remember from the endocrine system, which we just kind of added in this time around, the thyroid stimulates cells to increase metabolic heat production. So the thyroid, your T3 and T4, remember, your metabolic hormones. So your thyroid gland is going to stimulate T3 and T4, so that way your metabolism will increase to help generate more heat. So that's the part that we haven't really mentioned throughout the entire AMP1. We never really mentioned that, but be sure to add that in. Now, from these 3 together, that will result in body temperature increasing, which will bring you back to homeostasis. Now, if, for instance, your stimulus, so this is going to be this one right here, if your stimulus is too high, what's going to happen? Well, the temperature receptors are going to initiate heat-releasing mechanisms. So basically, they are going to be talking to your blood vessels, telling your blood vessels to dilate, to offload that heat. That's what these little squiggles mean. You're offloading that heat. And it's going to tell your sweat glands to start making sweat. Again, nothing new, I don't think. The thyroid gland may be a little new. We talked about it, but just putting it in this big picture here may be a little different. That thyroid gland stimulates cells to decrease heat and metabolic activity. So it's going to diminish the amount of T3 and T4 that are secreted to limit metabolic activity. And that is if the body temperature is too high. The collective group of these 3 events right here will result in body temperature decreasing, which will bring you back to homeostasis. Now, how does the body use mechanisms that the body uses to maintain temperature? So what kind of things can the body do to maintain homeostasis? You've got these 4 pieces. Make sure you understand the definitions of these 4. Radiation, convection, conduction, and evaporation. So let's first take a look at radiation. But before we do, let's understand the way heat moves. Heat always moves from an area of high heat concentration to an area of low heat concentration. So heat is actually going to move. That arrow is kind of moving the wrong direction there. I don't know why that's doing that. Heat flow goes this way. Always. It moves from an area of hot to cold. Here's the thing with cold. Cold is an absence of heat. So it's low heat is what that is. And an area of hot would be considered high heat. So cold is just the absence of heat. So in this scenario, I don't know why that arrow is going that way. That's really weird looking. Things are going to move from an area of high heat to low heat. So let's talk about radiation first. So you do need to understand the definition of radiation. This is one way the body is involved in heat exchange, moving things around. So this is the flow of heat without the need of an intervening medium. For example, you don't need to physically touch something. This is basically going through space. So an example would be, how does the Earth get heated up by the sun? Does the sun reach out and touch the Earth and heat it up? No, it's that radiation that travels through empty space to reach the Earth, and that's actually how the sun heats the Earth. This would be the same thing as you standing near a fire. Don't touch the fire, but if you stand near it, the heat from the fire radiates to where you are. Remember, it's going from an area of high heat to an area of low heat. And you guys have all noticed this, because if you're standing at a bonfire or something like that, maybe you're facing the bonfire, what you may need to do is turn around so your back is facing the bonfire because your front got too hot. So you turn around so your back is then facing the fire, so your back will then warm up. That's radiation. It's directly going to the source that is in line with it. This is about 60% of heat loss from the body is going to be lost through just straight radiation. Your body is going to offload heat through a process known as radiation. Have y'all ever heard of being picked up on thermal imaging or something like that? Ever seen Predator, the movie? That's radiation, being able to see that. Mechanisms of heat exchange, part 2. This is convection. This is what happens inside the center of the Earth as well. So we've got warm air rising, cold air falling. Warm air rises because it's less dense. Cold air falls because it's more dense. So it creates this convection current that happens. If you've got a pot on the stove with water in it, the water at the bottom closest to the flames right here, that's going to have an area of high heat. And remember, things go from an area of high heat to low heat. So at the top where the cold is, because it's further away from the flame, so things are going to move towards the area of high heat. And then when they get up here, they're going to get cooler and become more dense and fall. So you have what's called these convection currents that happens. This accounts for 15% of heat loss by the body is going to happen through this method. C, conduction. Conduction is transfer of heat by two objects that are in direct contact with each other. So this would be if you touched a pot on the stove. Let's go back to our picture here. If you were to touch the handle, that would be you getting heat from the handle. You're directly touching the handle. 3% of heat loss is through direct contact. So for instance, if you hold an ice cube, for example, again, things go from high heat to an area of low heat. And so that would be the heat from your hand is going to the ice cube. It's going to cause the ice cube to melt and your hand to be cool. Evaporation. So 20% of body loss, heat loss, is through the evaporation of water. So what's going on with that? You've got your sweat gland here that is making sweat because you're too hot. That sweat is going to accumulate on the surface of your skin. When it's hot outside, that heat is going to cause the sweat to evaporate, to turn into a gas, if it's hot outside. Now, if it's cold outside, the liquid isn't going to turn into a gas. Okay, that's why in the wintertime, that's really not going to happen. It's going to have to be hot in order for this to happen. So that liquid will then turn into a gas. Now, the quicker that things evaporate off the surface of your skin, the cooler you feel. So that's why, for instance, rubbing alcohol or fingernail polish remover, acetone, feels very cool to the touch, even though it's at room temperature, because it evaporates faster off your skin than, let's say, water does. Water doesn't evaporate very fast. It evaporates, but not very fast. That's why all of those three substances at room temperature, the rubbing alcohol and the fingernail polish remover, are going to feel cooler to the skin. That's why people take, years ago, to bring down a fever, they would take an alcohol bath because it would make them feel cooler. It would cool that skin off really fast. People who live in humid environments, like here in Northeast Texas where we live, we have a problem with evaporation. Because the air has so much moisture in it already, the sweat does not evaporate off of the surface of your skin because you have a high moisture content in the air already. The air can't hold any more moisture. So this water that's on the surface of your skin cannot turn into a gas and be part of the air because there's already too much in there. So if the sweat doesn't evaporate, you don't cool off. So that's why people in humid areas are at a higher risk for heat exhaustion and things like that because sweat doesn't evaporate in a humid environment. That's why they say, oh, well, in the desert, it's a different kind of heat. It is. It's a dry heat. So your moisture, your sweat can evaporate, cooling you off. So low humidity means you've got more evaporation possible. So when you're looking at, let's say, an infant who has just been born, you can see the umbilical cord still attached. They are having, they have a hard time controlling their heat in the body. So they have a hard time with that. So if you just put them on a table, you're getting heat through physical contact of the cold table leaving their body. You've got evaporation occurring, you've got convection occurring, and you've got radiation occurring. So again, they're going to be more at risk for losing heat and not being able to maintain body temperature. That's why it may be middle of the summer and that little baby's got footies on and is wearing a little cap on their head, again, to prevent radiation from occurring, to prevent that heat from just leaving the body. BMR, basal metabolic rate. This is the amount of daily energy expended by humans who are at rest. So just to kind of give you an idea how this all is broken down, the energy needs of the body, 60% of it is your basal metabolic rate, 30% of that's going to go for activity, and then 10% is going to go for temperature regulation. Factors that affect your basal metabolic rate. What is going to increase your basal metabolic rate? Well, a lean body mass, physical activity and exercise, growing, being male, height, the taller you are, stress, the more stress you have, digestion. These processes are going to increase basal metabolic rate. Now, what are some factors that decrease metabolic rate? Aging, things slow down when you get older. The more fat you have, the lower your metabolic rate is going to be, which seems kind of counterintuitive because you're like, well, I need it to be high if I've got a lot of fat so I can burn fat quicker. That's not how that happens. Starving and dieting, so constantly going, that's why you hear a lot of people who have, oh, I've been on this diet and that didn't work. Oh, and then I went over here and all I'm doing is still gaining weight. And that's because you're messing up that basal metabolic rate. Sedentary living, being female, and sleeping. All of these factors decrease your metabolic rate. Just kind of showing you the resting metabolism for a female is going to be lower than that of a male. That's why when you see calorie counts for a person, one of the factors that determines how many calories you should take in a day depends on gender and your physical activity. What do you normally do? So a nutritional calorie, abbreviated with a capital C, is the amount of heat it takes to raise, the definition, the amount of heat it takes to raise 1 kilogram of water by 1 degree Celsius. Know the definition. A nutritional calorie is the same thing as a kilocalorie. Okay, that's the same thing. So it's the metric system versus the Food and Drug Administration kind of thing. A person needs, again, 1,500 to 2,000 calories a day, depending on your basal metabolic activity, your basal metabolic rate. What's your body mass? What's your age? What's your height? What's your gender? What's your activity level? So what is a calorie? So this is kind of what I was talking about just a second ago. So a calorie, if you notice, if you were to take a look, we're looking at degrees Celsius right here, okay? So we'll just say this is 5 degrees, okay? 5 degrees Celsius is currently where that thermometer is. And this up here is 6 degrees Celsius. So it is and notice our water level hasn't changed. So it's the amount of energy it takes to raise the water by 1 degree Celsius. In nutrition, a calorie is the amount of energy measured in kilojoules to raise the temperature of 1 kilogram of water by 1 degree Celsius. So this water right here, it's giving you the mass rather than the volume, but that's 1 kilogram of water. The accumulation of an extra 3,500 calories adds 1 pound of weight. If an excess of 200 calories a day, so let's say you need 1,500 calories a day, you're eating 1,700 calories, 200 more than what you need, 1 extra pound of weight will be gained every 18 days. That's pretty amazing if you think about it. At that rate, if you keep this up, just eating 200 extra calories a day, at that rate, you will gain 20 pounds in a year. Now, the reverse of that would be true too, right? If you were 200 calories a day short, you would lose a pound every 18 days, losing a total of 20 pounds in a year. To lose weight, the number of calories burned per day. To lose weight, the number of calories burned must exceed the number of calories ingested. So again, there's a direct relationship there with how much food is ingested versus how much weight is gained or lost. So now let's take a look at food label and calorie calculation. So again, you're going to have access to a calculator. If you're taking the Respondus test, it'll be available on the Respondus platform. And then if you're going in to take the test in the testing center, you're going to need to either bring a calculator that you don't mind having cleared or use one of the calculators available at the testing center. You just need a simple, standard add, subtract, multiply, divide kind of calculator, nothing fancy or anything like that. So what you would be given is a nutrition label on the test. What I'm not going to give you is the total number of calories. So this information right here will be missing. Okay, so that won't be available on the test because that's what I'm going to ask you to calculate, is calculate the total calories. So what you're going to do is you're going to take the three, because they're not going to be highlighted, okay? So you're going to have to find the 3 energy yielding nutrients, which is going to be your fat, your carbohydrates, and your proteins. Those are your 3 energy yielding nutrients. You're going to take the number of grams of fat, multiply it by 9, the number of grams of carbohydrates, multiply by 4, the number of grams of protein, multiply that by 4, and add them up. So when we take the carbohydrates, that would be 25 times 4, that would be 100 calories from the carbohydrates. When you look at the fat, that would be 12 times 9, that would be 108 calories. When you look at the protein, that would be 3 times 4 for a total of 12 calories. Now you're going to take the 100, the 108, and the 12, add them up, and that will get you the total calories. And just kind of FYI, yes, alcohol that you consume also contributes to calories, as some of you all probably have heard. People who are alcoholics also tend to be diabetics because the volume of alcohol that they're consuming, again, that's going straight to sugar there, it actually provides 7 calories of energy for every 1 gram of alcohol. So that's why people who are alcoholics, they can drink alcohol and you're like, well, you haven't eaten all day, you haven't eaten anything. They're getting a lot of energy. I won't say nutrition, but they're getting a lot of energy, and that can be converted to ATP. So there's that. And it's also, not good for the body, but they are getting ATP. So be sure you can do that. So that's where that 220 calories came from. So be able to calculate that. And that concludes our nutrition chapter.